Okay, so new definition. Let X be a quaternion the norm of the quaternion X is the real number which we denote using the same symbols for absolute value, and this is the square root of the product of the quaternion X with its conjugate. All right, so now we turn our attention to the most comprehensive structure that can be studied in algebra, which is an algebra over a field. So an algebra over a field F is a vector space V over the field F together with a binary operation mapping two vectors back into the set of vectors called vector multiplication such that for every three vectors u, v, and w, and for every pair of scalars a and b, the following conditions hold. A vector times a sum of scalar multiples of two vectors is the same as the scalar multiple of the products the vector products, and a sum of scalar multiples of a vector of two vectors distribute over a single vector the dimension of an algebra is the dimension of the underlying vector space. So we will show that the quaternions is a algebra over the field of reals, but first we need to establish some lemmas. Let V be a vector space over a field F. Then the dot product satisfies the distributive law that is, for every three vectors u, v, and w in the space, we have that u dot, the sum of vectors v plus w, is the sum of the dot products u dot v plus u dot w, which is the same as the sum of vectors v plus w dot u. So proof: Let u, v, and w be three vectors. Then u dot, the sum, v plus w, is the sum of the products of corresponding components. So this is u sub I times the ith component of v plus w, the sum of the products of these components. So this is u sub I times the component of the vector v plus w, which is the sum of the components, v sub I plus w sub I, which is u sub I times v sub I plus u sub I times w sub I. This does distribute as these are now scalars. And so this is the same as u dot v plus u dot w. Now the dot product of the quantity v plus w dot u is the same as u dot, the quantity v plus w, as the dot product is commutative. And again, this is equal to the sum u dot v plus u dot w, which of course is the same as v dot u plus w dot u. And so the distributive law holds for the dot product. So new lemma. Let V be a three-dimensional vector space over a field F. Then the cross product satisfies the left and right distributive laws that is, for every three vectors u, v, and w in the three-dimensional vector space V, we have that u cross the sum v plus w is the sum u cross v plus u cross w, and the sum v plus w cross u is the sum of the cross products v cross u plus w cross u. So proof: let u, v, and w be three vectors in the three-dimensional vector space V. The ith component of u cross the sum v plus w is the sum of permuted products epsilon sub I j k, the jth component of the vector u times the kth component of the vector v plus w. This is epsilon sub I j k u sub j times the sum v sub k plus w sub k, as this is the kth component of the vector v plus w. And so we have epsilon sub I j k u sub j times v sub k plus u sub j times w sub k. This is epsilon sub I j k u sub j v sub k plus epsilon sub I j k u sub j w sub k, which is the ith component of u cross v plus the ith component of u cross w. And so u cross the quantity v plus w is equal to u cross v plus u cross w. Now, the quantity v plus w cross u is the negative of u cross the quantity v plus w, which is the negative of u cross v plus u cross w, which is the negative of v cross u plus the negative of w cross u, which is v cross u plus w cross u. And so the left and right distributive laws hold for the cross product. So as an example, we will show that the quaternions, which we will express as elements of the form x sub naught plus the vector x, where x sub naught is a real number and the vector x is a three-dimensional vector with real components. The quaternions is a four-dimensional algebra over the field of real numbers. So proof. We have already established that the quaternions is a four-dimensional real vector space So define vector multiplication as follows. For every two quaternions x and y, the product of x and y is the product of the quantity x sub naught plus the three-dimensional vector x times y sub naught plus the three-dimensional vector y, which is x sub naught times y sub naught plus y sub naught times the vector x plus x sub naught times the vector y plus the product of the three-dimensional vectors x and y, where this product of the three-dimensional vectors x and y is the difference of the cross product minus the dot product. So let x, y, and z be three quaternions. Notice the product of the three-dimensional vector x with the quantity a times the three-dimensional vector y plus b times the three-dimensional vector z is the cross product minus the dot product which is a times the vector x cross the vector y plus b times the vector x cross the vector z minus a times the vector x dot the vector y minus b times the vector x dot the vector z, which is a times the quantity x cross y minus x dot y plus b times the quantity x cross z minus x dot z, which is a times the product of the three-dimensional vectors x and y plus b times the product of the three-dimensional vectors x and z. Similarly, a times the vector y plus b times the vector z times the vector x is the cross product minus the dot product which is a times y cross x plus b times z cross x minus a times y dot x minus b times z dot x, which is a times the quantity y cross x minus y dot x plus b times the quantity z cross x minus z dot x, which is a times the product y times x plus b times the product z times x, where again x, y, and z are three-dimensional vectors. So now that the hardest part is done, I leave it as an exercise for you to verify that the product of the quaternion x with the quantity a times the quaternion y plus b times the quaternion z is equal to a times the product of the quaternions x and y plus b times the quaternions x and z, and the product a times y plus b times z times the quaternion x is a times the product of the quaternions y and x plus b times the quaternions z and x, and hence the quaternions is an algebra, a four-dimensional algebra, over the field of real numbers. Okay, so we'll end here for today. Next time we will continue to look at algebras over fields, and we'll demonstrate that the quaternions is a non-commutative algebra over the field of reals. So I hope you have enjoyed the 15th lecture. Thanks for watching.